Hello again, and welcome to another GCSE computer science theory lesson. This lesson is going to be on Unit 4, logic gates. So, logic gates, why do we learn about these in computer science? Well, because many electronical components are made from them, including CPUs and most things on your computer. So, pretty much everything electronic these days has some kind of logic chip or logic gates in them. If you want, I can try and bring up a diagram of the logic gates that you might find in your processor. And if we look at that, that is just absolutely horrendous. And that is a very simplified diagram. It doesn't go into a lot of detail. In reality, CPUs are even more complex than this. So CPU logic gates are even more complicated than this. Don't worry, we ain't going to learn about any of this stuff at GCSE. We are going to keep it really simple. Now, to start off with, I'm going to tell you about the most simple form of logic when it comes to logic gates. A piece of wire. Okay, I'm not joking here, but let's imagine we're sending some information down a wire. If we send a 0 down our wire as the input, we get 0 as our output, or hopefully. If we send 1 down our wire, we get 1 as our output. Are you with me? I know that's complicated, but generally speaking, if you send something down a plain wire with nothing on it, you should get out what you put in. You should. And let me try and illustrate this for you with some circuit diagrams. There we go, and I'm going to use this website called logic.ly, or Logically. And there we go, and should I buy it for $59? No thanks, I can use it for free. Alright then, so I'm just going to make this simple circuit here. So I'm going to take a switch. At the moment it is set to off. I'm going to have a little light bulb. I'm just going to put a wire across. So the switch is off and the light bulb is off. So 0 in, 0 out. Turn it on. 1 goes in, 1 goes out. So the switch is on, the light bulb is on. So that's what we mean by 0 in, 0 out, 1 in, 1 out. Okay, let's make things more complicated. We've got a magic little component called a NOT gate. And a NOT gate's job is to invert things. It makes things not happen. So it does the not of what you were trying to put in. So we put in a 0 and a 1 comes out. Or we put in a 1 and a 0 comes out. Let me explain that. Well, I say explain. Let me just give you a demo of it. Okay, so I'm going to put in a new switch. I'm going to put in a light bulb. And I'm going to search for a NOT gate. Here we go. And by the way, in the exam, you are expected to remember what a NOT gate looks like. So it's that little triangle with a little dot on the end. Looks like a Christmas tree. If you ever struggle to remember it, just think it's not Christmas. Okay, so if we turn the switch on, so our switch is on, the light bulb is off. If we turn the switch off, the light bulb is on. So there we go, it just knots everything that you put in it. It inverts things. Okay, so moving on to an AND gate. So this gets a little bit more complicated. We have 2 inputs into our device. So 2 inputs go into our AND gate, and you do need to remember this little symbol. So it looks like a big D. If you struggle to remember that, that's D for AND. We're going to have 2 inputs and then 1 output. So with an AND gate, both inputs, so input A and B, need to be turned on for the output to be turned on. Everything else is 0. And let me give you a little demonstration of this in action. I definitely recommend that you try this software out for yourselves at home. I just got it by Googling Logic Simulator. So we're going to take 2 inputs. They're both set to off or 0. So they're both set to 0. We're going to take a light bulb. That's going to be our output. I'm going to put an AND gate in there. Here's our little AND gate. So both are turned off. That stays off. We turn one on. It stays off. We turn the other one on. It still stays switched off. So it will only turn on if both A and B are turned on. That's why it's called an AND gate, because A and B need to be enabled for the output to be enabled. Okay, moving on to an OR gate. An OR gate is like an AND gate, but it is way more flexible. You just need input A or B to be turned on to get the output. So A or B needs to be enabled to get the output 1. So let me give you a demonstration. I'm going to switch this out for an OR gate. And you do need to remember this symbol. I don't have any ideas for remembering this symbol. Just remember that it looks a bit like the Star Trek badge, I think. Alright then, let's connect these things up. And definitely try this example at home. Okay, so at the moment, both inputs are off, both inputs are 0. If we turn on this one, the thing turns on. Or if we turn on this one, it turns on. But also if we turn on both of these things will turn on if either of them are enabled. So if A or B or both are turned on, the output is turned on. Another thing that you need to be aware of is that you can combine logic gates. So in this example, I've combined an AND gate with a NOT gate. So we're just going to do the standard logic for an AND gate, but we're going to invert it with a NOT gate. So if we take a look at the output here, we've got 1, 1, 1, 0. But with an AND gate, it's 0, 0, 0, 1. So that NOT gate does the job of flipping things around. So that NOT gate effectively inverts the final output. Let me show you with an example. Let's put an AND gate in there. So if we take a look at this, both things are turned off, the light bulb remains off. It won't turn on unless both are turned on. But if we add in a NOT gate onto the end, followed by a bulb, it now behaves in the opposite way. So it's turned on even though both things are off, and it still remains on unless we turn on both. If we turn on both, it then switches off. So it's behaving inversely. And for the topic of logic gates, I'm going to recommend a video game to you. And this video game is called Redcraft, and it involves a component called Mindstone. So if you want to practice logic gates and you want to make it fun, then download a copy of Redcraft and by all means play with a component called Redstone. So moving on, I'm going to throw you straight into the deep end with an exam question. And in the exam, they will ask you to list all of the possible inputs for this circuit, along with all of the appropriate outputs. So this is where it gets a bit challenging. What on earth does it mean by all of the inputs, all of the different input combinations? Another place where students will find this quite scary is because there are 3 inputs. Now we've done examples of a 2-input gate and a 1-input, but trying to juggle 3 inputs is quite tricky. So don't worry, I'm going to talk you through it step by step. And to help us out, I'm going to use Microsoft Excel just for the purposes of drawing this table. So first of all, we need to write down all of the different combinations of inputs for this question. And when we mean all the different combinations, we mean counting from 0 through to 7 in binary. Because 7 is represented by 3 binary digits, and we have 3 different inputs. Both can be 1 or a 0. Sorry, all of them can be either a 1 or a 0. So let's start off by writing out 0 in binary, followed by 1, followed by 2, followed by 3. And I'll tell you what I'm going to do. I'm going to show you a shortcut to write this out even quicker in the exam. We just write 0, 1, 0, 1, 0, 1, 0, 1, followed by 0, 0, 1, 1, 0, 0, 1, 1, followed by 0, 0, 0, 0, 1, 1, 1, 1. And there you have it. Those are all the numbers from 0 to 7 in binary. Okay, so up next, we need to start calculating the output of Z. And no one would expect you to go straight from 0 to the output. That is too difficult to do. So what we're going to do is break down the problem. We're going to divide this into smaller tasks to make things easier. And to help us with this, I'm going to use Microsoft Paint. So here you go, here's our logic diagram. This little point just after the NOT gate for A, I'm going to call this NOT A. And I'm going to make the font a bit smaller so it fits a bit nicely onto my diagram. Okay, so I'm going to call this position NOT A. So this position right by here is going to be called NOT A. And this position by here, I'm going to call B and C. And we're going to start calculating the results for these positions first of all. So I'm going to insert a column or two, and I'm going to call this NOT A. And so let's output the logic for NOT A. So if something is not 0, it is 1. And if something is not 1, it is 0. So there we go, there's NOT A already completed. For the next column, I'm going to do B and C. So the output for B and C. So we're looking at these two columns by here. So both of these values need to be 1 to have a 1 here. Are both of these 1? No, they are not. In fact, these two are both 1, so we call that 1. None of these have both columns as a 1, but this one does. So there's our output for this column. And finally, Z is just these 2 points ORed together. So we're just ORing together these 2 columns here. So is this one or this one lit up? Yes, it is, so we call that 1. Is this one or this one a 1? So we call that a 1. This one or this one? This one or this one? None of these are lit up, so that's a 0. That's also a 0, that's a 0, and that's a 1. And there you have it. There is your completed answer to that style question. So another type of exam question they could ask you in the exam to do with logic gates is a scenario-based question. So they'll give you a scenario similar to this one, and it is up to you as the student to draw the symbols and the logic diagram required for the situation. So in this example, we have some automatic doors, output Q, that can be opened by the activation of any one of 2 sensors, inputs A and B. There is an override security switch, input C. If the switch is enabled, then the doors will close. Now, this is a difficult question. The very nature of these types of questions is that they are supposed to be difficult. Don't feel bad about yourself if you don't understand the question. They are a tricky place to start. The only way you're going to get better at these style questions is with practice. So anyway, I'll talk you through this question, and then with a little bit of practice on your own, you will become confident with these types of questions. My point is, don't worry at the moment if you feel like you're not very good at these style questions, because the very nature of them is that they are indeed very challenging. Okay, so what I'll do first is I will answer this question using Microsoft Paint, and then I will recreate this question inside a logic simulator just to explain it in a little bit more detail. Okay, so what do we need first? There's going to be an output Q, and there's going to be inputs A, B, and C. So I'll draw those on. So inputs A, B, and C. And there's also going to be an output Q. Okay, what next? So the automatic doors, Q, can be opened by the activation of any one of 2 sensors, inputs A and B. Now this is a bit of a tricky question because they use the word "and" here. Well, this thing in brackets doesn't really have anything to do with the question. It's just pointing out that those sensors are known as inputs A and B. The "and" has nothing to do with the situation. This bit is implying that it is an either or situation. So as long as sensor 1 or sensor 2 is activated, then the doors will open. So we are going to have ourselves an OR gate. And by the way, in the exam, you will be required to draw these yourselves. So I'm just going to draw myself an OR gate. I do apologise in advance for the terrible drawing there. There you go, that's supposed to be an OR gate. And that's going to be connected to A and B. Brilliant. So if this question was out of 6 marks, you would probably have about 2 or 3 marks for this so far. We are not finished yet. There is more to this question. There is an override security switch. Input C. If the switch is enabled, then the doors will close. So notice that it says, if the switch is enabled, then the doors will close. So if the switch is on, so if C is on, the doors should be off. So we're going to have an inverter here. We're going to have a NOT gate. So we know there is going to be a NOT gate after C. Now, if I was going to grade this, I would probably call this 4 or 5 out of 6. There is something missing. These need to be connected up. And we can't just do that. They need to be connected by something. And in this situation, it is an AND gate. I will explain why this works in a moment. So, I'm just going to open up this website called Logically. You can buy a license for $59 if you want. Okay, let's make this an example. So let's get ourselves 3 inputs, so A, B, and I'll put C just a little bit further down, just to make it obvious. We're going to connect inputs A and B by an OR gate. And we're going to connect it up to an output. So this can be our output queue by here. And just to try and bring this back to the context of the question for you so it makes a bit more sense. They're automatic doors. Automatic doors, whether it be in a supermarket or a bank, there is normally a sensor on the outside of the building that causes the door to open if it detects movement. There's also a sensor on the inside of the building that causes the doors to open from the inside if they detect movement. So let's imagine this is the outside of the building. Somebody walks up to the door, it opens. Somebody walks up to the door from the other side, and the door opens. If both people are on the doors on either side, it still opens. So that's why it's an OR gate by here. Now, here is the override security switch. In the scenario of the question, when this switch is activated, the doors are going to remain shut. What if we just tried to connect this up to the doors? That is not going to work. We're going to need to use an AND gate to connect them. So let's connect up an AND gate. And you'll notice that our circuit has stopped working. The reason for this is this AND gate. This AND gate will only pass on a 1, so it will only this light will only be lit up if both of these inputs are 1. So if both of these inputs are turned on, only then will this light up. That's why it stopped working. So in this example, it is a NOT gate. So it's when this switch is turned on, then these should stop working. So let's delete that and replace it with a NOT gate. And let's connect it up to a switch. So here we go. Now our circuit functions as it should. The reason why we've got the NOT gate and the AND gate here is because if this is turned off, then we get a positive input by here. We get a high input by here, meaning that this cable is going to work just fine and pass things along to the light bulb. If we turn it on, however, so if we enable our override switch, this becomes low This becomes a 0, and therefore none of these work. There you go. That's everything you need to know about logic gates for the GCSE.